Hello, today I will talk about the final project of this course, that is mathematical statistics. So our subject is Johnson-Su distribution function, and our team members are Carla Águila Salamanca and me, Sebastián Flores. So let's start. I will talk first about the abstract. This poster addresses the subject of Johnson-Su distribution. Describe a system of frequency curves that represent transformations of the standard normal curve. Through this method, we can estimate the best parameters describing the active cases of COVID-19 in Mexico, since it has been shown to perform better than the normal distribution or any other. So now, to get into the context, I will talk about the introduction. So the current pandemic of COVID-19 caused by the SARS-CoV-2 virus presents a series of clinical, evolutionary, and epidemiological characteristics that make it a complex phenomenon. The world is going through a historic and unique event due to the advance of the virus and the pandemic, which generates impacts and challenges for the health, education, and cultural systems. Social and economic inequality and environmental and psychology effects are also present. The COVID-19 pandemic has generated a huge amount of data and is probably the best documented disease in history. Since the very beginning of the pandemic, many models have been proposed to understand the outbreak dynamics of COVID-19. This method illustrates how simple techniques can be used to solve otherwise complex problems, such as describing an epidemic wave.
Next, we're going to talk about some theory, and this is general information that we found about this distribution. The Johnson's SU distribution is a four-parameter family of probability distribution that were first investigated by N.L. Johnson in 1949. This is an unbounded and continuous probability distribution. It's member of the Johnson system, a family of four probability distribution that also include the log-normal distribution, the normal distribution, and the Johnson SV distribution. The U in the part of SU means unbounded, and the B stands for bounded. Bounded distribution have constraints placed on them, like weight, time, or weight maximum and minimums. Unbounded distributions like this do not have these restrictions. Johnson proposed it as a transformation of the normal distribution. And this is the transformation, the formula right here. That is phi multiplied by gamma plus delta times the sin O inverse, and this is all multiplied by the difference of x minus c divided by lambda. And applying this transformation allows us to get a unique curve to be derived for whatever combination of mean, standard deviation, skewness, and kurtosis occurs for a given set of observed data. The standard method of fitting Johnson curves is to use four coefficients defining a Johnson distribution, two shape coefficients that are gamma and delta, as well as a location that is the parameter c, and a scale coefficient that is lambda. To visualize it in an epidemic curve, we put the number of cases on the vertical axis and the time unit on the horizontal axis. The basic assumption is that each epidemic wave, called W, in a given country visualized by a cumulative epidemic curve, that is its cumulative number of infections in time, can be described as a 5-parameter scaled Johnson unbounded CDF. That these 5 parameters are scale parameter that is represented by the letter S, and the above mentioned moment's expected value, that is the parameter A, E, standard deviation that we represented with sigma, sickness by S, and kurtosis by K. And well, we have this function right here, that is the function W, depending on T, that is equal to S multiplied by F, that depend on the parameter that we mentioned before, that is E, sigma, S, and K, where T is the time measured since the day of the beginning of the pandemic, and the function F is the Johnson CDF with parameters delta, C, and lambda, assuming that the mean, the standard deviation, sickness, and kurtosis are equal to E, sigma, S, and K, respectively. Parameters S and K were expected to improve the curve fit at the tails of the epidemic wave if it was not symmetrical or heavy-tailed. Once the Johnson CDF were fitted, the basic parameters for obtaining the wave dynamics are these ones. That is the quantile, and this is the quantile of 2.5%, and this is the function F of 2.5%, and we have to do this exactly the same with the quartile 5% and the quartile 97.5%. In our experimental setup, we have that the method of fitting the Johnson CDF to the epidemic wave may be performed in 4 steps. The first step is smoothing the raw area. That is, it is supposed to smooth the data before the curve fitting process, especially when one is trying to perform curve fitting when one full epidemic wave is not observed. Although smoothing did not affect the fitting process to the full epidemic wave, it may be useful when fitting into the ongoing wave of infection because smoothing the data decreases the sensitivity on the numerical estimation method to changes in the starting point values, which in this case are more difficult to evaluate. The second one is visualizing the epidemic wave using the cumulative epidemic curve. This is recommended because the cumulative epidemic curve is a monotonic, which means non-decreasing, and a smoother curve than the epidemic curve. The third one is finding starting points. The main advantage of using an alternative fitting method is that at least 3 starting points for coefficient S, E, and sigma are intuitive and may be obtained visually from the cumulative epidemic curve, these make our work much easier. The last one is fitting using alternative sets of starting points. After visually selecting an initial set of starting points, it is recommended to perform fitting using other set of starting points from the evaluated intervals. The following graph that I'm going to shows the Johnson cumulative density function, that are the red lines in the graph, fitted to the data on COVID-19 trajectories, that are the cumulative epidemic curves. And well, we have here the graphic of Mexico and the active cases of COVID-19. And as we seen before, in the x-axis, we have the time, that in this case is counted in days, and in the y-axis, we have the population infected. In this case, we are describing it as a percentage. And this red line, it is the fitted curve of the infections in Mexico. And well, the function of this curve is E of t, that is 0.74 multiplied by the function f, that is depending on the parameters that we've seen before, where from this formula right here, we can identify basically the parameters where E is equal to 260.98, sigma is 59.30, S is 0.42, and K is 0.03, and well, S is 0.74. This indicates the parameters that we described before. And in this case, we have one infection wave, as we can see clearly in the graph. Only we have this peak of the infection in Mexico. And we have the fitted Johnson cumulative density function. And well, then we have some basic parameters of the first infection wave dynamics, where we calculated using Johnson cumulative density function fitted to the pandemic wave in Mexico. We have these parameters and its respective values, where S, that is 0.43, is the smoothness parameter of the fitted Johnson. P sub inf, that is 0.74, refers to the percentage of infections during the pandemic wave. The Q, 2.5%, indicates the day the infection wave started. The Q, 50%, indicates the day that the total percentage of infection during a given wave was reached. And the Q, 97.5%, indicate the day that the infection wave ended. Then we have other parameters such as M, that it means the day that the peak occurred, and that is 191. And TE, that means the duration of the TE, that is 86, means the duration of the wave increase. TD means the duration of the wave decrease. T means the wave duration. And finally, the letter A indicates the symmetry at the infection wave. Then we have, like, for example, in this, we can see the days, like the duration of the wave increase was 86 days and the decrease was 144 days. And well, as I mentioned, all these parameters gave us an interpretation of the graph that I mentioned already. To conclude our presentation, we think that the method presented here provides information about the dynamic of the spread of COVID-19 in Mexico, a country that we have the data and the daily numbers of infected cases. The curve of fitting that we obtain is a valuable tool to understand epidemic data around the world, and the main goal was to obtain easily interpretable parameters describing past trajectories of COVID-19 infection. This method, based on fitting COVID CDF curves to the cumulative number of confirmed cases, is straightforward, well-known, and easy to use. It yields curves that are extremely well fitted to the data. Thus, the basic parameters of COVID-19 infection dynamic obtained are easy to interpret and used in further statistical analysis by researchers from fields other than epidemiology, sociology, biology, and ecology. And finally, these are our references.